Okay, so let's start the morning session. Welcome everyone. The first speaker is Florian Herzig from University of Toronto, who's telling us for the multi-Langlands correspondence with Galois.
Thank you very much, and I thank the organizers for inviting me to this great conference. I certainly didn't expect to speak in a room with a view of the Great Wall. So I will speak about towards a mod Langlands correspondence for GL2, and just for orientation, I want to briefly talk about the general Langlands picture. So generally, in the Langlands picture, there's an automorphic side and a Galois side. And if you remember Weil's talk from the beginning, on the automorphic side, you see things like modular forms on the upper half plane that have a lot of symmetries, functions on the upper half plane with a lot of symmetries. So objects that eventually are objects of representation theory and harmonic analysis. And on the other side, you see, for example, elliptic curves and their associated Galois data, Galois representations. So these are objects of algebraic number theory and of arithmetic geometry. And there are different settings where you can do a Langlands correspondence or a Langlands reciprocity, namely the most classical is in the case of number fields, like the rational numbers and finite extensions, or it's analog over a curve of a function field of a curve over a finite field of characteristic P. And then there's a corresponding local story. When we have a curve, we can look infinitesimally near a point, and similarly for a number field, we can complete at a point. And in the case of a number field, we go to either a p-adic field like QP, the real numbers, or the complex numbers. And in the case of a function field of characteristic P, we go to a completed function field, like a Laurent power series ring. And generally, the local story is easier, but the two are perfectly compatible. So that will be good to keep in mind going forward. So let me briefly talk about p-adic fields, because I'm not assuming that you're an algebraic number theorist or something related. So a p-adic field is obtained from the rational numbers in the same way that you obtain the real numbers, by completing at an absolute value. And in this case, the p-adic absolute value is defined by this concrete formula that p to the n times any fraction that's relatively prime to p is p to the negative n. So in other words, something that's highly divisible by p becomes very small in the p-adic topology. And when we complete, we obtain this very nice field, which is topologically, very simple, but also maybe strange if you're used to the real numbers. Namely, we get something, yes, it's still locally compact, but on the other hand, it's totally disconnected. And also algebraically, we have a description where we Zp, the ring of integers, is obtained, the elements of the norm less than or equal to 1 are obtained as an inverse limit of the usual integers modulo p to the d, where d goes to infinity. So it's a compatible system of congruences, so it captures all the information for this prime p and nothing else at other primes. And then qp is obtained by inverting p. And zp is compact, and it's a much simpler ring in some sense than Z, because it's a discrete valuation ring. It has a unique maximal ideal, and it's still a principal ideal domain. And then once we have a p-adic field, we can, for a Langlands program, we need p-adic groups. So for this talk, I will only talk about the general linear group. So let me denote G, the group GLN QP, and slightly more generally after. And K is GLN of ZP, of this ring of integers of QP. This is a maximal compact subgroup. And because of this unusual p-adic topology, it's actually an open subgroup, not just compact. And there's this decreasing filtration with compact open subgroups that define the topology near the identity. And those are the congruent subgroups, the matrices that are one, the identity modulo increasing powers of P. Those are essentially P groups. Yes. And then we also have two other groups that play a role later on in the talk. First of all, there's the Iwahori, so-called Iwahori subgroup, which is those matrices in GLN ZP that are congruent to an upper triangular matrix modulo P. And inside, so those are finite index subgroup. There's the Iwahori, and then there's the pro-P Iwahori, which are those matrices, that integral matrices that are one modulo, that are an upper triangular unipotent matrix modulo P, and that's actually a P-Silov subgroup of K. So these groups will keep playing a role in this talk, especially K1 and K1 and I1 and K. So in the talk, I will not just talk about QP, but also about finite extension fields of QP. And everything is kind of the same as before, just the notation changes. Instead of ZP, we now write OF for the ring of integers, which are the elements of norm less than or equal to 1. So I use the same notation. And now I want to talk about the classical local Langlands correspondence. So it's local, meaning we use a p-adic field, F. And so there are several ways of stating a classical local Langlands correspondence, but I will use this way, where I choose another prime L not equal to P, and consider L-adic Galois representations. And so this is the Galois side of the correspondence. We have Galois representations of this p-adic field F with coefficients in the L-adic field of dimension n. And on the other side, we have irreducible representations of GLN, the same n, and the representations are of over QL bar, over the same coefficient field. And strictly speaking, I should say we only see those representations that admit a GLNF stable lattice, ZL bar lattice. But that if you want to know what smooth and admissible means, so smooth means that the action of GLNF is continuous when you give the vector space the discrete topology, which is equivalent to saying that every vector is fixed by some compact open subgroup or congruent subgroup KD. And admissible is the additional requirement that all of these fixed spaces, the KD invariant subspaces, are finite dimensional. So it's a nice finiteness condition, a natural finiteness condition. And so in the classical local Langlands correspondence for GLN, everything is known. So for n equals 1, that's classical from the 1930s, perhaps. That's local class field theory, because in that case, basically, there's a group isomorphism that explains the bijection between irreducible representations, because if we have, everything becomes abelian. If we have representations into GL1, they factor through the abelianization of the Galois group. And on the right-hand side, if we have representations of the abelian group GL1F, they're automatically one-dimensional. So the groups are essentially isomorphic. There's one slight difference, that the left-hand side is compact, so we have to take a suitable compactification or profinite completion of GL1F, but that is it. And when n is bigger than 1, it gets vastly more complicated, and it's a very long story that was finished by work of Harris and Taylor around 2001 or so, and NER around the same time. And then a few years later, Scholze gave another proof of the local Langlands correspondence. And then much more recently, for general G, there's a new geometric approach by Farag and Scholze so it works for general G. It's not completely finished in the sense of getting a bijection, but I will not comment more on that approach though, but you may hear more about it next week. And what I wanted to say too is, as far as I know, there's no completely local proof of this local Langlands correspondence for GLNF. There's always an interplay with the global story in order to get such a proof. Okay, so now there's a natural question: what happens when we replace the coefficient field of characteristic 0, QL bar, by other fields? So this was considered by various people over the years. So the first thing to be considered was field of characteristic L, FL bar, let's say. And in that case, such a correspondence is known as mod L Langlands. And this was first established by Viñeras as a consequence, or in relation to the classical Langlands correspondence by kind of reducing modulo L. And later also a different version by Emerton and Helm. What's interesting for my talk is when we go to either the field of a p-adic field instead of an L-adic field where L is not equal to P, or especially when we go to a characteristic P field like FP bar. And in those cases, when one calls these p-adic or mod P Langlands. And in contrast with all the previous things I discussed, this is still mostly hypothetical, or a dream, as some people would say. And but n equals 1 at least is still okay, for the same reason as before, that the group isomorphism gives you the bijection of representations as you want. Okay, so any questions up to this point? Feel free to ask anytime. Yes, I mean, basically, classically, you would actually formulate it over the complex numbers, but then you have to replace the Galois group by something, by a slight variant. But yes, thank you. So now for mod P Langlands, the hope is one has so a correspondence of a nature that I wrote down before, but more precisely, what one hopes is that so one kind of gives up the irreducibility on the GLN side, but at least one could hope that any Galois representation can be mapped to an admissible smooth representation in a way that like a fully faithful like any injection that satisfies some natural properties. And I will explain why one drops the irreducibility on the right in a moment by looking at the case of GL2QP. So this is the only case essentially the only case when n is greater than 1 where something is known, and here things are perfectly known. And this is a long story starting with conjectures and work of Breuil, and then a long series of works by Kolmez and Kizin, Emerton, Pashkunas, even in the p-adic setting, even though I will focus on mod P. So I will just briefly review something of the features that you may have already seen in Kolmez's talk, but so there are two cases have a two-dimensional representation. It can be reducible or irreducible. And in the reducible case, we have an extension of two characters, chi1 and chi2. And what we would associate, like even if you were to guess from the classical Langlands correspondence, you take those two characters, you transfer them using class field theory to the other side as a character of QP cross, and then you use those to construct an induced representation from the Borel subgroup. And in the classical story, it doesn't matter which way you order the characters, you generally get the same representation, and that's the irreducible classical Langlands correspondence. But in the mod P story, those two representations don't have anything to do with each other, so you are kind of forced to see them both. And so you have to give up the irreducibility on the right-hand side of the correspondence. And the other thing that happens mod P that we didn't see alladically was that we generally do get any chi1 and chi2 admit non-split extensions. And so we have to see something else happening on the right-hand side if we want to get an injection. And what we see is that the extension class on the Galois side is reflected in the extension class on the GL2 side. I'm suppressing small special cases, for example. Yes, so these extensions correspond. So those representations are known as principal series representations. And in the irreducible case, it's in a way more similar to the classical story that the irreducible representations correspond to irreducible supersingular or supercuspidal representations. Yeah, so for GL2QP, everything is essentially known, and it's a very beautiful story, both matp and p-adically. But the focus of my talk will be now for the group GL2F. The surprising thing is when you replace QP with F, things do change drastically. Unlike the classical local Langlands correspondence, where it doesn't matter too much which F you take. And so for the purpose of my talk, I will just focus on the simplest case where F is an unramified extension of degree, which I denote by little f. So unramified just means that P generates the maximal ideal of the ring of integers. So these are the simplest extensions. And let me highlight two challenges that arise in this case. So the first one is that if you just think like for GL2QP, that in the case of irreducible Galois representations, we just want to have a bijection between all supersingular representations and all irreducible Galois representations. That immediately fails because there are far more irreducible supersingular representations once F is not equal to QP. I could say more about that later if you have questions. And then the other challenge is that the irreducible supersingular representations, they are no longer describable in a finite amount of data. In the case of GL2QP, it's very nice. The classification was done by Bartel, Livni, and Breuil. But in the case of, as soon as you pass to a degree 2 extension, it becomes vastly more complicated. And let me just say a few words about the first part, the first item. How do we actually construct representations of GL2F? So this is again strange from the point of view of maybe complex representation theory. What is done is let the group GL2F act on its analog of symmetric space, the Breuer-Titz building, which is a tree, and it acts transitively. And then if you saw Serre's book, that tells you that the group G is an amalgam. So it has a very simple presentation in terms of two subgroups. So K is the GLNOF that I had before, Z is the center, I is the Iwahori subgroup, and N is the normalizer of the Iwahori. So those are some particular subgroups, but the idea of Pashkunas and Pashkunas is that you start with a finite dimensional representation D0 of KZ, you embed it into its injective envelope, so injective as in abstract algebra, and so this is some infinite dimensional representation now, and you restrict to the Iwahori, to this finite index subgroup, and find a way to extend the action to the normalizer of the Iwahori. So this just slightly, you just extend it to a slightly bigger subgroup, and then in this way, once you extend the action by the amalgam property of that I wrote here, see that omega becomes a G representation, and which contains the D0 you started with by construction. So you can take the subrepresentation generated by D0, and under some mild conditions on D0, you get irreducible representations in this way. And the problem is you have a lot of flexibility in this construction, and so that's how you get kind of too many representations in this way as soon as you leave GL2QP. And so one issue is this construction is highly non-canonical because we use injective envelopes which are not canonical, just unique up to isomorphism. Yes?
Yeah.
Well, usually to construct supercuspidal representations, you still induce representations. So there's a way to compactly induce representations from some compact mod center subgroup, and you can construct, there's some very clever constructions that have a long history, and all the irreducible supercuspidal representations of GLNF were constructed in such a way by suitable induced representations. That's a good question, but I mean, you already know everything for GL2F. I mean, it's relatively simple in the case of adic or complex representations. That's a good question. I mean, this construction still makes perfect sense for QP, but somehow you can easily classify all the irreducible supersingulars, and yeah, just very simple. Okay, so next I want to discuss so how would we ever know how what the mod P Langlands correspondence should look like if we don't know how to locally construct these representations? So the key is from the global world. And so this will be used throughout my talk now. And so I will, in the global setting, we have a way to construct representations of GL2. And I will first discuss this in the case of GL2 over Q or QP. Namely, you can start with a modular curve of level M. So that's a classical object in the world of modular forms. It's basically a moduli space of elliptic curves where we trivialize the M torsion. So the elliptic curve is an abelian group. We look at its M torsion as an abelian group and fix an isomorphism with Z mod M squared that always exists. And then as soon as we have a moduli of such pairs, then GL2 acts on the right-hand side. And so GL2 Z mod MZ acts on the modular curve of level M. And in the limit, when we pass through n times all the powers of P, we get a tower of those modular curves. And we get an action in the limit even of GL2 QP, not just ZP, as you might expect, even of GL2 QP. And the other good moduli space is that this one makes sense over the rational numbers. And in this way, we get the Galois action, which commutes with the GL2 action. And by the way, this also makes perfect sense with the adic coefficients. And people have used that in order to construct and prove local Langlands correspondences and instances of global ones. But in the mod P setting, there's an amazing theorem of Emerton around 2011 that works even in the p-adic setting, which says that if you start with a global Galois representation that's irreducible and modular, then if we harm that, if we use the Galois action to and this representation R to construct a GL2 QP representation by taking the harm, we do in fact get the mod P Langlands representation associated to this Galois representation once we restrict it to the local Galois group. So we have the global Galois group. Inside, we have this decomposition group, the local Galois group. If we restrict, then the two things match up. So here we have mod Langlands correspondence, and on the left, we have the globally defined representation. Okay. So here everything is known, both sides are known, but the great thing is the global, this global definition makes perfect sense in great generality for GLNF. So what I'm going to do is I'm going to take Emerton's theorem and I generalize the left-hand side, and this will sort of guide us in what we should expect about the mod P Langlands correspondence. Because all these Langlands correspondence, they always show up globally in this cohomology, any kind of Langlands correspondence I mentioned. So as I write here, pi of rho, we don't know it, but I can define a substitute, which is this pi global rho, which I define as in Emerton's theorem. I will not give you the completely precise definition, but you can imagine roughly what I would do. And I just keep in mind that I'm really abusing notation here, because the left-hand side I write rho, but on the right-hand side I'm using a global representation that restricts to rho. So there are a lot of choices I'm making and I'm suppressing, but I just use this suggestive notation because we hope that this pi global rho is actually the pi of rho. Maybe not everybody is convinced of that expectation, but so far we don't know a reason why it cannot be true. And So we do hope that all the choices we made in this global definition are actually irrelevant. So we get a unique locally defined representation. And the other thing we hope, in analogy with the case of GL2QP, is that, well, we don't get an irreducible representation. We cannot hope that it is, but at least we hope it is of finite length, just like in the case of GL2QP. And there are more precise expectations that come from the work of Brian Pashkunas, namely, if rho is reducible, something weird happens where we don't just expect a two-principal series that we certainly do expect to see, but we also expect to see f minus 1 supersingular representations in between. So this is maybe very weird, and I could say later why one kind of needs something else. And what do I mean with these lines in between? I mean possible extension classes. So it's no longer going to be semi-simple in general, just like in the case of GL2QP. So if we have a split extension class, we would expect direct sums. And if we have a non-split one, we would expect all of these to be non-split extensions, so we get a uniserial representation. And moreover, we hope that this correspondence is compatible with respect to semi-simplifying on both sides. And lastly, in the irreducible case, we still expect to get something irreducible and supersingular, or they expected a long time ago. So these are the expectations, some of the expectations for GL2F. And now I want to talk about what's known about these globally defined representations. So am I going too fast? Any questions? Yes, so this is only for unramified F. For ramified F, one would expect, I think nobody has seriously studied the ramified case. There's a lot less that is known in that setting. So again, certainly you would expect to see these principal series, but I don't know exactly what to expect in general. I mean, maybe I can say that for GLNF, where F is unramified, we have also made some more general conjectures about what you might expect, what it should look like. In the unramified setting, it does seem to be, some things are significantly easier. It's easier to make guesses. Any other questions? Okay, so the first piece of information about this globally defined representation, sometimes I will just say pi of rho to keep it short, because there is no pi of rho, and so there's no possible confusion, hopefully. So the first part comes from the weight part of Serre's conjecture, Serre's modularity conjecture that connects modular forms and global Galois representations. Namely, it talks about, so what it gives for you is the so-called K-socle of this representation pi of rho. So in other words, what is the K-socle? We restrict pi of rho to the subgroup K, which is GL2 of OF, so to this compact open subgroup, and we want to know what are the irreducible subrepresentations, or equivalently, what's the maximal semisimple K subrepresentation of pi of rho. And the answer is that it is a direct sum of finitely many explicitly describable representations, and in some sense explicit, in many cases completely explicit. So let me make a few comments. So these sigmas, first of all, they are all distinct from each other. There are no multiplicities. And these irreducible K representations, more precisely smooth K representations, they are automatically representations of K modulo K1, because K1 is a P group, and all the representations from now on are over a characteristic P field, which means by basic representation theory that P groups only have, the only irreducible representation is the trivial representation. So any irreducible K representation, unlike over the complex numbers, is forced to be trivial on already K1, which is a p-sub group. And so they become representations of the finite quotient group, which is just GL2 of the residue field, which is GL2 of Fp to the F. And for example, one can describe them explicitly in terms of representations of the algebraic group GL2. There are certain symmetric powers twisted with field embeddings, and they have dimension at most p to the F. And now, if you compare now what I say in part 1, so these are all finite dimensional, but pi of rho is infinite dimensional. That means, surprisingly perhaps, for if you're used to complex representations, if you restrict pi of rho to this compact subgroup K, it's highly non-semisimple. Like over the complex numbers, everything is semisimple, but here it's highly non-semisimple. You just have finitely many irreducible subrepresentations and sort of lots and lots of extension classes, extensions with other ones and so on. All these irreducible pieces are finite dimensional. And yes, that's from admissibility. Because K1 acts trivially, so it has to be inside the K1 invariants, which are finite dimensional. Yes, thank you. And maybe I can also say, I wanted to say that this pi of rho, when you define it globally, one nice thing is that it's automatically admissible. Automorphic facts. And the last thing I just wanted to mention is the definition of W rho that I'm not giving here is very subtle. It was conjectured by Buzzard, Diamond, and Jarvis in the early 2000s. But it only depends on rho. Again, it's defined in a global setting, but it was supposed to be purely local, and then it was proved to be by G. Leo Savitt and G. Kissen in around 2010 to 2014 or so, maybe a bit earlier. So this was kind of the first piece of information. And by the way, this is kind of the reason why you knew to begin with that many supersingular representations constructed by Pascunas could not be part of the pi of rho, because they have K subrepresentations that do not appear in this list of Buzzard, Diamond, Jarvis. You have a lot of flexibility in constructing representations with things in this K-socle, but they do not match this prediction, at that time prediction, and now theorem. So this is the first piece of information. So it's just, in a way, a tiny, tiny piece of this pi of rho. Next, we go slightly further. So I want to discuss this work of Li. There are three papers, Li, Mora, Schran, Yongchun Hu, who is here, Yitong Wang, Haohan Wang, and Yan Li, Dan Li. And this determines the K1 invariant. So that's slightly bigger than the K-socle, as I was just mentioning. So the K1 invariants inside pi of rho, still finite dimensional. They determined this as K representations. This was an expectation of Florian Pascunas that this is true, Florian Pascunas. And D0 rho can be defined in the following down-to-earth way. It's the largest finite dimensional representation of K modulo K1, which is GL2 over the residue field, such that its K-socle is as before, as in the weight part of Serre's conjecture, and it's still multiplicity free. So it has some non-trivial extension classes, but you don't see any Jordan-Hölder factor reappear higher up in the representation. So it's again purely local, and as we would like to see, because we would like that the left-hand side is purely local. And the key input, and actually to some extent this is already a key input in the previous theorem, comes from the Taylor-Wiles method. So more precisely, to prove this theorem, just before these were proved around 2015 to 17, 18, these Taylor-Wiles patching functors were developed by Emmett and G. Savitt, building on the method originating from Wiles' proof of cases of the Shimura-Taniyama conjecture, and work of subsequent work, including work of Kissen as well, led to these improvements in the Taylor-Wiles patching method led to these patching functors in the work of Emmett and G. Savitt. basically, traditionally, some particular setting is fixed in the Taylor-Wilds method, some particular weight and some particular level, and roughly speaking, and in the patching functor construction, this is sort of removed, and you do all the possible patchings at the same time. You allow arbitrary weights and levels, and whenever you input something here that corresponds to some fixed weight and level, then you get out the more traditional Taylor-Wilds patched module. And maybe in a nutshell, what does Taylor-Wilds kissing patching method do for you? So the issue is that if you start in some particular finite weight and level setting of modular forms, elliptic curves, etc., the issue is everything is really complicated. You have these complicated Hecke algebras and you have complicated Galois deformation rings, but the method, the patching method, is an extremely clever way to pass to infinite level where everything becomes much simpler. In particular, the Galois deformation ring becomes a very simple ring, typically. For example, in our setting, regular local ring. And one nice thing about the functor is that it's exact, and it allows you, as always in the Taylor-Wilds method, it allows you to recover things from classical finite level by modding out by suitable ideals. So if we mod out by the maximal ideal of R infinity of this local ring, a complete, actually regular local ring, if we mod out by this maximal ideal and dualize this, then we get a piece of pi of rho. So it allows us to probe pi of rho with different representations W. And the other thing we need to know that comes from the Taylor-Wilds method is that for nice W input modules, we know that the output is Cohen-Macaulay and we can bound its support. So you have geometric information about the output, and you kind of need to play with this in clever ways to get useful results like this one and the previous one. And I draw a picture now. What does D0 rho look like? This is maybe not easy to find in the literature. So here, if rho is semi-simple, in that case, this set W rho consists of 4 elements defined by Bazard-Diamond Jarvis. So I draw it in 2 different ways. On the left-hand side is kind of the abstract graph representation. On the right-hand side is the actual submodule structure. So I remind you that W of rho is the case Sokal of the representation. It sits at the bottom. That's the sub-representations. Here you actually see the submodule structure. And then these other weights sit on top with non-split extensions. So the lines represent non-split extensions on the right. On the left is just all the Serre weights of a fixed central character and all the possible extensions that are allowed between them, X1s between them. And then I draw the other extreme where rho is as non-split as possible. In this case, W of rho just has 1 element, and then the K1 invariance, this D0 rho, is a bit more complicated extension of that. But in terms of the graph, it's just all the neighbors, essentially. You see all the possible non-split extensions that abstractly exist, they really occur inside the representation. So this is sort of the next. It's that small piece of pi of rho of this infinite dimensional representation, but it's going a little bit further than just the semi-simple sub-representation that comes from the weight part of Serre's conjecture. And then, so in more recent joint work with Christophe Roy, Yongchuan Hu, Stefano Mora, and Benjamin Schran, and in parallel, work of Yongchuan Hu and Haohan Wang from 2020, we went one step further. So it looks like a very small improvement, technical improvement perhaps of what was known before, but I'll try to explain that this was a very crucial improvement. So let me denote by MK1 the unique maximal ideal of this completed group algebra. So it's essentially a group ring. And since we're in characteristic P and K1 is a P group, this is a local ring. It has just 1 maximal ideal, and MK1 is the notation for it. And if we take MK1 torsion, this is also the augmentation ideal, so this just recovers the K1 invariance. And if I take mk1 squared torsion, I get something bigger. Basically, the largest thing that is an extension of two k1 invariant things. And now we can define the analog of D0 rho by the same definition as before, except what you do is you don't force it to be k1 invariant, but you just say it's killed by mk1 squared. Otherwise, the definition is the same as before. So again, it only depends on W rho. It's purely local. Doesn't depend on any global information. It's still multiplicity free. And we proved the analogous theorem. So as I said, looks like a small technical improvement. The method is still using patching functors, of course, but in a lot more intricate way. It was a bit surprising it was even possible, because we need to prove that when we input a rather large finite dimensional module, a projective envelope of some particular irreducible modulo mk1 squared, into it, that we get a cyclic R infinity module for all sigma in the K-circle. So why, okay, small picture, it just extends the previous picture. So we just go slightly further. These white dots are what were added compared to the previous picture. And I'm no longer drawing the submodule structure. I mean, here it would be easy. You just cut this picture into these 4 parts and you rotate them. But in the other one, it would get a bit messy to draw all these possible extensions between them, but all of them occur. But why is this useful? I have to explain now. So the consequence is that we can understand something that was conjectured for a while, or at least hoped to be true for a while, namely that the so-called Gelfand-Kirillov dimension of pi of rho equals the degree of the field, which is f. What does that mean? So one way of expressing that is that the dimension of these, I told you for admissible, that means when we take invariance under any congruent subgroup, we get some finite dimensional space. So it's natural to ask about the growth rate when d goes to infinity. And this grows roughly like p to the df, where f is this Gelfand-Kirillov dimension. So now to explain how our theorem comes into this is I need to pass to the dual side. So there's this nice duality between smooth representations or admissible representations, and you can pass to the Pontryagin dual, and you go from something discrete here to something compact on the other side. That's often convenient. It's perfect duality. So we get a finitely generated module over this compact local group algebra. It's again a P group, so it's local, which I call lambda. And M is the unique maximal ideal of lambda. And here I recall this I of 1 was this finite index subgroup of K, which is the one matrices that are upper unipotent when you reduce modulo P. This is the Silov subgroup of K, one of the Silov subgroups of K. And now what's sort of the basic idea, the basic connection with the theorem is that in the theorem, we got the mk1 squared torsion, which tells us about sort of the K structure of the representation. So one twist in the story was that we had to go from K, which was kind of obtained more easily from the Taylor-Wilde story, to the I structure. And we could, this is some representation theory. We go from the knowledge of the mk1 squared torsion to the knowledge of the m cubed torsion for this Pro-P-Vahori subgroup. And knowing so previously what was known was just the m torsion, but the m cubed torsion gave us a lot of mileage. It was very valuable because when we passed to the associated graded module for this dual module here, pi dual, we obtained that it is killed by certain degree 2 polynomials. The degree 2, to see that, we needed the m cubed torsion. So it's killed by a certain explicit ideal in the graded of this completed group algebra. And the key thing then was, so we could use this first point to get these relations. Yeah, okay, I'm not explicitly giving them inside GRU of lambda, but the key thing was that this ring we obtained is now, first of all, it's commutative, which is way simpler. And because we started with this non-commutative group and group ring. but it's also of Krull dimension F. And Krull dimension F is what we can link back to sort of non-commutative dimension F and therefore to Gelfand-Kirillov dimension F. So previously what was known is it's at least F. That's relatively easy to obtain, I think. But the upper bound is very, very hard. And this is the only case outside GL2QP where it is known still. Okay. And now, in the remaining part of the talk, I want to discuss more recent progress of, it's the same authors as before. So we recently obtained in 2 stages, first 2 years ago and then this year, that the representation pi of rho is of finite length. I'm suppressing some technical conditions here, but in reasonable generality, we proved that pi of rho is of finite length, this globally defined representation, as was hoped for a long time. And so this we knew already 2 years ago, that if rho is irreducible, then pi of rho is irreducible. This one was a bit easier. And it uses, but it still uses as input something from the previous theorem. And the other thing we now know is that if we have a split representation, then pi of rho at least has some kind of splitting. It's this, first of all, it's a direct sum of those 2 expected principal series from the hopes before, and some supersingular representation in the middle, which has length at most f minus 1. And if you remember, the hope I mentioned from Poyam-Pashkunas before is that the overall length is expected to be f plus 1. So we prove its length at most f plus 1, f minus 1 plus 2. Sorry? Yes. Yeah, I think you can just pass the subquotients, it's still fine. Because it's still going to, basically the associated gradient will still be killed by this ideal, and you get the upper bound. I mean, anyway. And then in the non-split case, we can get the non-split extension pi 0, pi prime, pi f with same pi 0, pi f and pi prime of length f minus 1. But moreover, in this case, we can also prove that pi of rho is uniserial, as was expected. So we may not know how many pieces there are in pi prime. We know there's at least 1. I can also say that. So pi prime cannot be 0. That's sort of easy to see from the weight part of Serre's conjecture. But it could just be 1. Well, hopefully f minus 1, though. And some natural questions that are left open at this point are, do we really get length f plus 1? So do we really get the maximum here as equality? And the other question is, if pi of rho is semisimple, sorry, if rho is semisimple, is pi of rho also semisimple? So this is left open in case 2. And this, at the moment, it does not seem to be easy to answer because you have to construct maybe more. It's subtle to prove something is semisimple. And then maybe in the last few weeks, we have evidence for pi of rho is compatible with semi-simplification. So this is specifically in the case f equals 2, we get the nicest result. So let's take rho to be a non-split reducible two-dimensional Galois representation. We can look at the corresponding semi-simplified one where we put 0. And then what we know from our theorem is that both pi of rho and pi of rho semisimple have length 3, exactly 3, because in that case, that's the only case where we really know the exact length when f is 1, as was previously known, and f is equal to 2. That's the new case. So we know we see the same pi 0 and pi 2. Those are the principal series representations. We know it's uniserial on the one side and a direct sum on the other side. But we have pi 1 and pi 1 prime in the middle. And we would like to know those are the same up to isomorphism. And at least what we get now is that the K1 invariants of these two representations are the same. And also that the associated gradient as a module over the completed group algebra of the Propiva-Hori are the same as a graded module and with the I action. So So at least once we split extensions, we know these are isomorphic. Well, once we split lots and lots of extensions and only consider the I action. So let me now, in the last part of the talk, say something about the proof. So it gets a little bit more technical at the end. So the representation, this is the theorem I want to discuss, that the finite length result. So the key thing is that we can show that any subrepresentation pi prime is determined by its K1 invariance. And that one allows us to conclude finite length because the K1 invariance will have to lie in the K1 invariance of pi. And the K1 invariance we know, and this is a multiplicity-free representation, it only has finitely many K subrepresentations. So this allows us to get finite length. To get the more precise bound, we need to think carefully about what the possibilities are for the K1 invariance. But this can be done by some representation theoretic analysis. But I want to focus on the just purely finite length result. So a crucial input is another theorem we proved recently, that we determined the whole associated graded module of pi of rho as a module over the completed group algebra of de Probit-Bahori. I will not give the precise definitions, but we conjectured this 2 years ago, but now we are finally able to prove that, give an explicit determination of the associated graded of pi of rho. I mean, in other words, how you can think of that on the representation theory side is we restrict to the Bahori, and we look at the Sokal filtration, like you look at the maximal subrepresentation, that's semi-simple, you quotient out by that. You look at the maximal subrepresentation, that's semi-simple, and you keep going. And so we determine all the layers in this filtration. Not the extensions, but all the layers. And I will not say anything about the proof of this because it is relatively technical. But at least maybe it's easy to get a map from right to the hard part is to prove that this is actually, we get a map, a surjective map from right to left, and it's hard to prove it's injective. And here, this ring R is this commutative quotient we saw in the Gelfand-Kirillov theorem, and the rest is some explicit information which I will not tell you the precise definitions of. So this is a crucial input, and I will show you in a moment. So now we start with some arbitrary subrepresentation of pi of rho, pi prime. Then we get a corresponding quotient representation pi double prime. And we pass to the dual side. We use Pontryagin duality. We take just a full F bar linear dual and get modules over the group algebra. So it reverses the arrows. We get pi double prime dual mapping to pi dual mapping to pi prime dual. And these are filtered modules for the maximal ideal in the group algebra. And we pass to the corresponding associated graded modules. The tricky thing whenever you work in exact sequences is that you have to take the induced filtration on the left. We don't get the adic filtration. That's one of the headaches often. And then from this, we get the diagram as follows. So in the middle, we have the theorem from the previous page. We determined this module explicitly. So this n represents the other side in the theorem on the previous slide. So we have this isomorphism in the middle. And then on the left and right, so we have to kind of guess the correct answer by sort of verifying, when we look at this composition here from n to the graded of pi to the graded of pi prime, we have to verify enough explicit relations to get to the optimal answer, the optimal quotient of n that you should see here. But this is really something explicit. And we get a corresponding exact sequence in the end with explicit modules n prime, and then double prime. And one crucial thing is that this definition of n prime only depends on the K1 invariance. It doesn't see anything else about pi prime. And And then the last part is, I can just give, I cannot give you the real argument, but what goes into it is that we use a cohomological act duality on the level of group algebras to go from the quotient representation pi double prime to a sub-representation of pi. That's using the fact that this globally defined pi has, I should maybe have said pi global rho here instead of pi. This uses the fact that this pi is self-dual in the cohomological sense. And then we also use that this n prime is a Cohen-Macaulay module. So in order to check this map is injective, you only have to verify things on the level of irreducible components of the support. So then we check that this is an isomorphism, and that implies the result, because this tells us that the associated graded only depends on the K1 invariance of pi prime, on its K1 invariance. And then it's relatively easy to see that this implies that pi prime itself only depends on the K1 invariance. And then we deduce finite length from that. So I will stop here.
Are there any questions? Hi, I just have a question that I know this representation is
Okay, good question. So you, so here, I mean, the Hecke algebra, in classical representation, you construct the Hecke algebra to describe representations, but this is kind of all based on the fact that you have H measure. And here we don't have H measure in characteristic P because the group is essentially a P group. You can't divide by P, so we cannot use such techniques. But we have group algebras, so they play an important role. I mean, yes.
Another question is that
well, it's a pro-P-Silov subgroup, so it's a very natural subgroup to consider if you do modular representation theory. And I mean, at the beginning, actually, when we were working on this Gelfand-Kirillov theorem, we did not work on it from the point of view of the Iwahori. I mean, one annoying thing is, in some sense, the K1 is much nicer because it's what's called a uniform pro-P subgroup. So its associated graded is already commutative, and it's a polynomial ring. So in some sense, it's a much nicer ring, but But on the other hand, like if you want the associated graded of pi, it becomes much simpler when you go to this Iwahori setting. But this took us a long time to realize. Yeah. But I think in this in the mod P story, I mean, sometimes results are more about the K and K1, and sometimes more about Iwahori and I1. Yeah. Mm-hmm.
case?
Yes. I guess. No. I mean, we know something about, we know a lot about them, like it's some K structure and I structure, but no, we have no purely local description. Yeah, it is kind of weird that certain supersingular ones should appear in associated with irreducible Galois representations and certain ones with reducible Galois representations, but apart from information like the K-socle and things like that, we don't have a good representation theoretic way of distinguishing them. Or the ones that that should not occur at all, unfortunately. I think maybe there were some hopes in the past that, I mean, I guess it could still be true that there are other representations that have different Gelfand-Kirillov dimension, but but at least the ones that occur globally, they all have dimension f.
Let's speak again.